Yeah, thank you to the organizers for having me and to organizing this really wonderful conference, and to all of you for coming. Today I'm excited to talk about some very recent work that about sort of resource efficient ways to form unitary and state K designs, and particularly coming from a more sort of many-body physics kind of way of thinking about how one can realize some interesting circuit architectures to realize intrinsic randomness in quantum many-body systems. And this is work that's done with some really amazing collaborators. I wanted to highlight. Unfortunately, I couldn't find pictures for all of them, so I decided not to include pictures for any of them, which is, I think, fair. So Yuzhen Zhang, who's a student, I think is in the audience, and then Yimu Bao, who's a postdoc at KITV, and Yingfei Gu at Tsinghua, and it's all summarized in this work, designs for magic augmented Clifford circuits. So the story that I'm going to be telling you today is, in my mind, it's very simple. It involves a lot of structure and a lot of introduction to the subject of maybe state and unitary K designs. But the sort of punchline for the intuition, at least my own intuition, is actually relatively brief. But the consequences, I think, are I think pretty interesting. And actually taking that intuition and proving something useful, which is sort of the standard for showing that something forms a unitary or state K design, is a non-trivial task and relies on the heavy lifting of some really amazing collaborators. So, okay, so let me just move on and first discuss the need for randomness. So uniformly Haar random gates or states on a large number of qubits provide a very important ingredient in two very different areas of physics and quantum information. So for many of you, and myself included, I think of Haar random gates or randomness as being a theoretical tool for studying very structured quantum many-body dynamics. So an example, or there are many examples, not just in condensed matter, but also in high energy physics, where a sort of quantum many-body dynamics is modeled by some kind of random process, right? So one prototypical example of this is the Hayden-Preskill protocol, where a black hole is modeled as a random unitary. This is really to address the question of the black hole information paradox. If I throw some unknown k-qubit state into that black hole and it radiates away Hawking radiation, and that's modeled by random unitary dynamics, then how much radiation does Bob need to collect before Bob can determine what state Alice threw in there? That's sort of the question that's addressed in this paper, right? And a random scrambler being a good proxy for a black hole. Okay, so that's on that end, and also in quantum many-body physics, we think of models for thermalization or far from equilibrium quantum many-body dynamics as containing some universal features, and many of those universal features are apparent if we consider really unstructured quantum many-body evolution, where the only ingredients that we preserve are locality and unitarity. We can add in other ingredients like symmetries back in to see what other structures emerge. And then we can try to find these structures in a structured, in a given instance of a quantum many-body evolution, right? So that's kind of bootstrapping universal structures that arise in random systems in order to study something that's unstructured, and that has a long history in physics, not just in the study of quantum many-body evolution. Of course, here we're using randomness as a crutch to study something structured. In quantum information, we're often interested in doing the opposite, right? Which is one might be interested in generating a truly random state or a truly random unitary gate, and that's intrinsically useful. And that's intrinsically useful for quantum algorithms. Or for validation of near-term quantum devices. So one might be interested in demonstrating a quantum advantage via a task like random circuit sampling, which requires generating gate sets that are truly random. Maybe there are algorithms for doing tomography that are better than just doing the naive quantum state tomography on a large subregion. And these sample-efficient algorithms rely on the application of a random unitary gate. Of course, randomized benchmarking is also another algorithm here. One thing I didn't mention on the slide, but I think is important just to tie things together, is also the subject of deep thermalization, which the conference organizers, I think, have been actively involved in. And that, I think, it doesn't fit into really many-body dynamics, or it does a little bit. And it fits into many-body dynamics, but it also includes measurements. So their state ensembles are generated in a many-body system by doing measurements on a complementary region, and those state ensembles can also resemble random states, right? And when they do, we say that those ensembles deeply thermalize in some quantitative way, okay? Now, exact preparation of uniformly random Haar ensembles of unitaries on a large number of qubits using local gates is extremely challenging, right? So here's a physical limitation I'm going to put in, which is that we can only generate these highly random unitary gates in a real quantum simulator or in a NIST device using local operations. And okay, this is also true in an analog simulator. It's very challenging because it requires exponential circuit depth. Why does it require exponential circuit depth? There's just a very simple counting argument, right? So if I want to generate a random unitary on n qubits, there are exponentially many real numbers, essentially, that I have to specify in order to write down that unitary. If I apply a local set of gates in my quantum many-body system, there's only polynomially many parameters that specify each time step of that dynamics, right? So then, okay, just what circuit depth do you need to get an exponential? Well, you need exponential circuit depth, right? So that's the basic argument for why you need exponential circuit depth. It's just counting, right? And that's true for more general gate sets as well, that you can get away with this kind of counting argument to tell how how quickly you can generate a uniform ensemble. So that's a problem. But then, true randomness, that is to say, like, exactly reproducing the Haar ensemble on n qubits is maybe not the thing that we actually want, right? Because, in applications, we only really want to think about quantum algorithms or situations where we're querying a random unitary or a random state some finite number of times, right? And so, in that respect, we don't need what we're approximating as a random unitary to reproduce every moment of a truly Haar random unitary, but just some finitely many moments, right? Okay, and here are pictures of two different quantum algorithms, just abstracted out, where one might be querying a random unitary in some adaptive way. So here I apply a random unitary, I query it again at a different time, and in between I may do some kind of operations that depend on the specific unitary that I've actually implemented. On the right-hand side, we have random states, and these random states are, in this picture, it looks like they're being queried at different times, but really you can see that, I can query them at the same time also. There's not really a distinction on the right-hand side between querying states at different times or in parallel. On the left-hand side, it doesn't really look like you can rewrite this quantum algorithm so that it looks like you're really applying the unitary U multiple times at the same time, because there are adaptive protocols that are applied in between, right? So that seems to suggest that sort of adaptive querying of a random unitary may be a little bit different than parallel querying, and we'll get to that in just a second. Okay? So what's an example? So if sample-efficient schemes for tomography, so shadow tomography, this is in a paper by John Preskill and others that I mentioned earlier, one might want to do some improved tomography on a quantum many-body system, and one might do this by implementing the following protocol. You say want to measure a highly non-local observable in some subregion of a quantum many-body system, and to access that highly non-local observable, a more efficient way to do it than to just try to access every matrix element of this density matrix is to first apply a random unitary to the state before measuring in a computational basis, right? And this can be used to form an estimator of the state. So you can imagine that there's a measure and prepare quantum channel, which is this channel n that I'm writing down. You do local measurements, and then you write down what you think the state was, given that the inverse of the unitary that you applied will map what you observed into what you might think the state was, right? And that gives you some estimator for the state row. But what controls the sample efficiency of a scheme like this? Well, one thing that would control that is basically like the variance of the observables that you actually measure, over many runs of this kind of this experiment, right? And that variance is going to be sensitive to whether the unitaries U, which are drawn from some ensemble epsilon, form a K design for some sufficiently high K. Okay, the variance being sensitive to some high moment of this ensemble, right? And of course, you might want to apply a very highly non-local unitary in this protocol, because maybe if you're measuring the fidelity of a quantum many-body state with respect to some other many-body state, which is an incredibly non-local observable, scrambling your system might be useful before you perform local measurements. Okay? Great. So So let me just say that this motivates a broad question about efficient ways in which we can generate unitary gates or states on n qubits, which approximate the kth moment of a Hart-random gate, k being the number of times I want to query these gates or states in a quantum algorithm. And before I get to some definitions of this, which are, these are, everything I'm saying now is like, definitely just from the literature. I just want to sort of formally define what a unitary state k-design, which is exact, actually is, right? And these ingredients will be relaxed, these statements will be relaxed when we define approximate k-designs, okay? So as a definition, a unitary k-design, I should think of as a quantum channel, right? So I should think of an ensemble of unitaries, which I'll call epsilon, I draw the same unitary from that ensemble k times, and I apply it to some state, some density matrix, right? A unitary k-design is an ensemble epsilon that reproduces the first k moments of a Hart-random unitary, which is to say that this channel is exactly the same as the quantum channel that you would obtain if you applied a truly globally Hart-random unitary, right? So this is to emphasize that this is a property of a quantum channel, right? And it's a property of a quantum channel, which means it's true for all input states into that channel. So it seems like a very challenging thing to sort of check. Okay, that's a unitary k-design, and this is true up to the kth moment. And when I say that every observable here, that these two channels are equal, that just means like any observable I measure on the left side matches that on the right, and those observables can be entangled across the k copies of my system. They're not just disentangled across single copies. The second statement is a state k-design, which I've written in such a way as to emphasize the fact that this is a more relaxed condition. So unitary k-design is a property of a channel acting on any input state. A state k-design is just a property of a state that's obtained by applying this quantum channel to a specific input. And in this case, I will take that to be just a product state, right? So I take a product state and I apply a unitary drawn from this ensemble to k copies of that product state to generate some density matrix, right? So this is a quantum channel, and now I have an output state. And I want to say that this output state is exactly the same as the one that I would obtain if I applied a Hart-random unitary to the same product state, right? Okay, and here sameness is just saying that every observable measured on the left and the right are exactly the same, okay? Of course, like I said, these are very hard to produce, right, for very large k. So what are approximate designs? So to say that something is an approximate design just means that the observables that I measure in this setup just match approximately what I would get from the Hart ensemble. But there are two very important notions of approximation. One is what's called an additive error design, and that means intuitively what you think, which is that observables sort of match what they would, their Hart-random values, but within some additive error epsilon, okay? And how does this work for state k designs, right? So for a state k design, the fundamental object is this density matrix on k copies of my system, which I'll call rho epsilon. What tells me, whether an observable is taking on its Hart value to within some error epsilon? Well, it's the trace distance, right? And the trace distance tells me that the trace distance tells me there is an observable that actually saturates this, appropriately normalized. So bounded trace distance is like saying that you have an additive error state k design, right? Okay, so generalizations of the trace distance basically form the different measures of designs for additive and also what I'll get to in a moment, relative error designs, but they get more complicated to think about. So this is, of course, the trace norm is something that we're used to thinking about as a norm for quantum many-body states, but to study additive error designs for unitary designs, we have to think about a superoperator norm, right? Because what I said was that there are two channels that are very close to each other, which means that any input that I send into the channel gives me the same output to within error epsilon, right? So really, this norm that I'm defining on the left, the diamond norm, is, you should think of it as kind of like the trace distance, except that I'm sort of maximizing the left-hand side over all inputs, right? So I throw in every input that I can, and then I maximize the trace distance, roughly speaking, and then, that has to be less than epsilon, okay? Okay, in practice, it's a little bit more complicated. There's an auxiliary Hilbert space also that's involved in this definition to stabilize this norm, but okay, that's more or less what it is a souped up trace distance, for, maximized over all inputs. And then finally, there's the notion of relative error designs, and this is the term used in the literature, but I would just say these are designs where observables match within multiplicative error, okay? Why do I care about this? Well, first of all, there are observables that within additive error, can be, their difference can be extremely small within these two ensembles, but they don't actually have the same qualitative behavior, right? Like a simple example is the entanglement of a subregion in a Hart-random state, or the purity, is going to be exponentially small in the size of the subregion, right? Now, the entanglement or purity in some other state ensemble could also be parametrically small in that subregion, need not be exponentially small, but what this tells me is that, as long as those two quantities are both parametrically small in system size, I can have an additive error design, right? But if I take their ratio, it can be extremely large, right? So a multiplicative error can, with respect to multiplicative error, those are not good designs. And that also tells you that this is just a stronger notion than additive error designs are. So relative error designs imply additive error, imply small additive error. And to formulate this formally requires introducing some operator and superoperator inequalities. I won't go into this, but these are basically sufficient conditions that basically tell me, that when I have an inequality like this, that just means that the right-hand side minus the left is also a positive map, and here that it's a positive operator, and those conditions are sufficient to guarantee that these observables across these two ensembles match to within multiplicative error. Okay. Now, here are sort of the main results. So the main results that we have are basically trying to understand circuit architectures which form state and unitary K designs, but while minimizing two different things. One is circuit depth, right? Because that might be something you don't want to make exponentially large. But the second is something else, which is non-classical resources, okay? We think of certain unitary gates as being very classically efficiently simulable, like Clifford unitary gates, free fermion gates, so Gaussian free fermion gates are also fall into that category. There are others. This follows from the Gottesman-Nil theorem. But these Clifford unitary gates cannot, of course, allow us to do universal quantum computation, and indeed they only form unitary 3 designs, right? So they can't really spoof the Haar ensemble at, for high moments. But then you may ask, how many non-Clifford gates are actually required in order to form a unitary or state K design, right? So that might be something you want to minimize if you want to actually try to simulate your noisy, quantum simulator dynamics on a classical computer, and maybe to benchmark what you're doing, right? Now, this idea of minimizing circuit depth in the formulation of unitary and state K designs is a relatively old subject, and it goes back more than a decade. But I just want to emphasize this is building on some very recent, exciting developments, which really motivated our own study, which is basically just saying that, over the past, 13 years or so, there's been an exponential reduction in the depth required to form relative error unitary K designs. Originally, it was believed that approximate, like I said, exact K designs require exponential depth. In 2012, it was shown that approximate K designs with small relative error only require linear depth in 1D. And then more recently, it was shown that they only require logarithmic depth, and even more recently, there's some other results, right? So this exponential reduction in circuit depth is kind of interesting, but, it would be great to understand the non-classical resources that are also involved. Okay. Our results are basically the following. Just to summarize, that it's actually relatively easy to form additive error state K designs and unitary designs also with bounded relative error with fairly few non-classical resources. Okay, and let me just to summarize what the result is. So our results are that in a one-dimensional circuit architecture where we have n qubits, a local Clifford circuit which has depth of order log n. Followed by just a constant number of magic gates, which scales with k, which is the moment of the Haar ensemble I want to mimic. That's actually enough to form an additive error state K design. Okay, it doesn't form an additive error design if I have no magic gates at all, and magic is just my term for non-Clifford gates. And this is actually true for k as large as poly n. Okay. I'll explain why this is the case in a moment, but it's maybe pretty striking that the sort of amount of magic you need is sort of just a drop in the bucket compared to the amount of classically simulable stuff that's going on in the circuit. And the second thing is, if I want to talk about relative error state and unitary designs, well, then the total circuit depth can actually still be fairly minimal. It's only logarithmic if the moment that I'm approximating doesn't scale with n. log n. But the number of magic gates that I need is much larger than when I have when I'm just forming additive error state in unitary designs. The number of magic gates, you can think of it as just like a single depth 1, or in this case depth 2 circuit, right? It's sandwiching the Clifford circuit. So this is the circuit architecture. So the number of gates I need still scales with n, but the depth is relatively minimal. Okay. Great. So let me try to explain to you maybe what I think is in my mind the core intuition that goes behind some of these results, specifically for additive error state designs, and it also informs how we think about relative error state and unitary designs, and that comes from what I'll call the statistical mechanics of random circuit ensembles. So this is my many-body physicist way of rationalizing this kind of intuition, though people who've worked in this field probably have all sorts of other ways of thinking about this. These results and also the StatMech picture imply certain no-go theorems that certain circuit architectures cannot create state and unitary designs with bounded relative error, which is kind of interesting for those of us who are interested in trying to understand what kinds of ansatz for wave functions, Clifford augmented MPS, for example, are actually good at mimicking very random states in Hilbert space. Okay. But the core message here will be this StatMech model of random circuits, which I'll get to right now. Okay. So I want to come back to this quantity that I wrote down earlier. So I have a state in a d-dimensional Hilbert space, and let's forget whether or not it's a product state. And I have just some ensemble, which is not the Haar ensemble of unitary gates, right? To think about state K designs, the object of interest is this quantity, right? Which is I apply the unitary U drawn from this ensemble to K copies of this state independently, and then I obtain some kind of density matrix, right? Okay, and I want to compare observables in this state versus what I would get if I applied the Haar random unitary, which is globally Haar random to this state. Now, if this ensemble epsilon is actually the Haar measure on the unitary group, then there's a nice structure that emerges when one actually thinks about this density matrix or any observables that you compute in this state, right? And that comes from a statement that's known as Schur-Weil duality, so that's maybe the mathematical way of thinking about it, and I'll give you maybe a sort of physics intuition for it in a moment. But so the Haar measure on the unitary group is the unique left and right invariant measure on U of D, and all that means is that this state, when this script E is the Haar measure, that this state is invariant under the application of K copies of any unitary on the left and the right. Okay, this is the property of the Haar measure, and it's the unique measure that satisfies this. Okay, what does this mean? Well, this actually means that that this state actually has a very special property. The state lives in what's known as the commutant of the unitary group. That is, the kth order commutant of the unitary group is the set of operators that commute with any set, k copies of any unitary for all unitaries that are in UD. And this commutant is just spanned by permutations. Why is it spanned by permutations? Is a very intuitive way to think about this, which is that I have k copies of my system, and I have a symmetry of those k copies, which is that I can obviously exchange them. But you can maybe hand-wavingly think that that's really the only symmetry that remains that defines the commutant when you have random unitaries, right? That can do anything unitary in Hilbert space, right? So that is to say that this state is going to be some convex sum of permutations, where pi sigma labels these permutations on k-fold copies of my Hilbert space. Okay, how do I understand this intuitively? Well, the elements of the permutation group that arise of the commutant really describe kind of pairings of Feynman trajectories across multiple forward and backward evolutions of the state, right? So I have k forward copies of my state, k copies of the bra, and k copies of the ket. And the idea is that, each of these copies, you can think of it in some path integral description as accruing a random phase as it evolves under the application of a unitary, right? And the phase is random, obviously, because of this random ensemble. But those phases have to kind of constructively interfere in order to give a contribution to this density matrix. And that constructive interference basically requires that paths are paired across a bra and a ket, right? And that pairing leads to this phase cancellation, and that pairing is precisely the element of the permutation group. That's it. Okay, this is a powerful statement, I think, and has lots of applications in the context of quantum many-body dynamics. As just an aside, if we consider, as I mentioned at the beginning, sort of an IID set of Haar-random unitary gates, which define a local unitary evolution of a quantum many-body state, then doing this kind of Haar averaging to compute, some property of k-fold copies of this state, which could be some generalization of the purity, right, Renyi entropies, etc., that maps onto some observable, which after doing this average, can be thought of as an observable in a model of statistical mechanics of permutation spins, where these spins are labeling in space-time the pairing of this quantum many-body system of the paired trajectories that constructively evolve. Okay, so how do we understand, using this picture, that order log n depth Clifford circuits with, say, just a constant number of magic gates can suffice to produce state ensembles that resemble the kth moment of a Haar-random state? And here, I'm just going to, flash again the definition of an additive error design, right? To epsilon approximate additive error, right? Which is to say that the trace norm is very small. Just use a very simple, norm inequality, which is to just say that this one norm is upper bounded by basically the two norm up to some factor that involves the Hilbert space dimension, right? That two norm, it turns out, is very easy to calculate, right? Because it's just the trace of, say, the difference of these guys squared, which looks like a quantity that many of you have seen before. It's, in this case, what I'll call the state frame potential. It's more or less related to the purity of each of these states, right? Okay. You might think that this box inequality that I've written down, where the left-hand side is what I want to upper bound, is kind of useless because the right-hand side involves a fact of square root of the Hilbert space dimension, right? But it turns out it's actually quite useful, and the reason is that the frame potential, if I remember that, it's basically the purity of each of these states is exponentially small in the Hilbert space, right? So actually the right-hand side is some order one number, and if I can bound this difference, I can actually get a control on the epsilon that shows up in the additive error. Okay. Similar results hold for unitary designs, but where this dimension factor of Hilbert space can't be tamed so effectively to get some useful statement about the circuit depth and other resource requirements for these designs. Okay. So now we want to consider a quantum circuit composed of random Clifford unitary gates, and now the StatMech model that sort of emerges when we do a random average over Clifford unitaries is more complicated than that of Haar-random unitaries. Well, why is that? Of course, if I take k copies of any quantum system, which is identical, I have a sort of bulk permutation symmetry of that system. That's true even if I take random Clifford unitary gates. But the Clifford commutant just has more structure to it. There are more operators that commute with k tensor powers of some arbitrary element of the Clifford group. And I'll label this set of objects which form the Clifford commutant sigma of k. So this is the commutant on k tensor powers of a Clifford unitary. Of course, the symmetric group is a subset of this, right? As a subgroup of this. The commutant isn't a group, but the symmetric group is a subset of this because I can always permute the different copies, and that's an invariance of my system, right? Okay, so now what do I do? What's the strategy for forming additive error designs? And this is the sort of physicist argument. So what I want to do is I want to take this StatMech problem for Clifford circuits, and I want to make it look like the problem that I get in the StatMech description for Haar-random unitaries. How do I do that? Well, I have a 1D circuit architecture. The StatMech problem that I'm describing lives basically in two dimensions, where the second dimension is determined by how long I evolve for in time, right? So the depth of the circuit dictates the height of this StatMech problem, and the length of it is determined by n, which is the number of qubits, right? So, okay, one thing that you would say is like, the strategy here is basically I want to increase the depth of this random Clifford circuit so that the StatMech model that describes it describes the ordered phase within the Clifford commutant subspace. The Clifford commutant also includes the symmetric group. And it turns out within the StatMech picture that when you introduce non-Clifford gates, those are kind of like a symmetry breaking field that basically polarizes the StatMech model within the symmetric subspace, right? So the depth of the circuit is determined by the depth that you need in order to order in the StatMech model within the space of the Clifford commutant. And then the number of magic gates you need is determined by how much of a symmetry breaking field you need in order to polarize within the symmetric group, okay? Yeah. Actually, well, should I take questions now or should I? Okay, yeah, maybe yeah, go ahead. Yeah, sure.
So does K, the magnitude of K matter in some way?
Yeah, so as I mentioned, K dictates the number of magic gates that I need to apply, right, in this circuit architecture. So, but if K is a constant, that's a constant, right?
Right, but like large K versus small K,
No, well, it doesn't change the result that I mentioned as long as k is less than square root of n or so. Yeah. Okay. So since I'm running out of time, let me just flash the StatMech intuition, and then we can maybe go into questions. So how does this work? So of course, a 1D StatMech problem with local interactions, we don't think it should have an ordered phase, with some with short-range interactions if I'm at any non-zero temperature, right? And so, of course, that means in this context that a finite depth random Clifford circuit shouldn't order within the Clifford commutant subspace. But if the depth scales with n in some favorable way, then you can basically order, and it's as if you're cooling the system to zero temperature as you take n to infinity. What is that optimal depth? Well, it's basically like taking the depth to be order log n, which is like inverse temperature being order log n in the StatMech model, right? So you take n to infinity, that, you can convince yourself if you just take your 1D classical Ising chain that scaling temperature like, 1 over log n, as you take n to infinity, will take you to the ordered state, right? So that's what I'm doing in the first step. That justifies why the depth should be order log n. And then the second step is basically, now that I've ordered within the Clifford commutants, how many non-Clifford gates do I need to apply in order for the bulk of the system to be polarized within the symmetric group, right? And that's just determined by a sort of free energy argument. And here I'm just going to be borrowing mathematical results about the Clifford commutant, which I honestly do not know how to derive, but these are recent results, which are basically just tell me how many generators of the Clifford commutant do not live within the symmetric group, right? That number of generators scales exponentially in k squared. That's just a result that I'll quote. And then there's a kind of energy entropy argument, right? So basically the entropy of the subspace that I need to sort of kick up to higher energies grows like k squared. And so you might think that in a StatMech description that those states need to be given an energy penalty that also grows like k squared. It turns out in this StatMech description that every magic gate you add in gives you an order 1 energy cost for every element that does not live within the Clifford commutant. And that gives you the order k squared scaling. That's it, right? So this argument is actually pretty general. At least it tells you that it doesn't rely on a particular form of the circuit architecture, but if you want to actually do this seriously, there are only very specific circuit architectures where we can actually show that this is the case. Okay. I think I'm out of time. So I'm going to just flash up a sort of central result that kind of ties together all of the ways that we think about state unitary designs with low magic usage and Clifford gates. And the central result in the paper is basically what I'll call the gluing lemma for Clifford circuits, which is formalizing this intuition that at log depth, the random Clifford circuit looks like it's going to zero temperature, right? And I have to go to zero temperature, but I want to also bound the errors as I go to zero temperature, and that is what justifies this. So it's basically a condition under which the product of overlapping approximately random Clifford gates resemble an approximately random Clifford gate on the whole system, right? That's basically it. And this is really a rigorous treatment of this first condition. And once that first condition is established, then everything else kind of follows relatively straightforwardly. Okay, so I think I will get to the rest of this in the question session if there are fewer than optimal questions. But here are my questions. And so my questions are basically sort of motivated in part by this StatMech picture. So one is like, a lot of the argument that I mentioned was fairly general, like the specific circuit architectures that I'm drawing, which involve a log depth Clifford circuit followed by a certain amount of magic, like they are architectures where we can actually prove something rigorously. But at least for additive error state designs, it seems like where you put the magic and how you form this Clifford circuit maybe is not like it's not that sensitive. Like you can still get a state design in the thermodynamic limit. Okay, so that's one question. The second is how these StatMech arguments generalize to other non-universal gate sets. I think that's kind of an interesting question. So we know that the Clifford commutant has this, structure. Of course, other non-universal gate sets like, free fermion random gates, you get some kind of StatMech description with a continuous symmetry, not a discrete symmetry. And so how you get Haar randomness from that, it might be the case that breaking that symmetry requires sort of more non-free fermionness, which would be kind of interesting if it actually means that the non-free fermion resources you need to generate Haar randomness are actually a lot worse than for Clifford gates, right? The last thing is really how these StatMech pictures generalize. It's been known for some time that, for instance, time reversal symmetric dynamics, like for orthogonal K designs, you can't form sublinear depth approximate designs to bounded relative error. How that shows up in the StatMag picture is very confusing. The symmetry group of the StatMag model just goes from the permutation group on k elements to 2k elements. It's not that different, the bulk StatMag problem, but somehow these arguments must break down in some way that we don't understand. So with that, I'll end and thank you for your time. Yeah.
Yeah, thanks for the nice talk. Yeah, question, Suwon.
So when you say magic gates there, that's depth or the number of gates?
Oh, that's actually the number of gates. Yeah.
And that does not cover even the all boxes, right?
Yeah, it doesn't. For additive error state designs, it doesn't even have to cover the full system. It's just applied in some local patch of your system.
I see. Also for the bottom case, relative errors.
Yeah. So for bottom error, for the bottom case, I'm just talking about now. This circuit architecture looks actually like this. So the purple is the magic gates. They're applied everywhere, and it's so here I'm talking about circuit depth, not the number of gates. So there's a constant magic depth that's applied. So,
I have an actual question. So
yeah.
So one of the reasons to separate Clifford and magic is relevance to the experimental realizations.
Honestly, so our first interest was to try to understand if there's how classical these state ensembles are or unitary ensembles are, how much non-classicality is needed to generate Haar randomness. The experimental relevance might be that, if I want to actually generate a state design, and if I have a classically simulable ensemble, right, then it might be easier for me in an experiment to actually benchmark what I'm doing, right?
Yeah, but my actual question was,
yeah.
When you say magic gates,
yes,
is it okay to have non-randomized fixed magic gates like key gates?
Yeah.
Or do you have to randomize? Do you assume Haar random gate?
Yeah,
when you say magic gate, do you actually mean Haar random gate or the specific
key
gate?
Here we prove the statement for local Haar random gates, but the argument that I mentioned is not specific to those gates being Haar random. It could be just
is that like your intuition or the provable thing? Because
we haven't proven that. So the proof is only for the case where the magic gates are themselves drawn from an exact design on like some finite number of qubits. Yeah, right. So that's kind of an open question, is whether we could prove that for, yeah.
Yeah, hi, thank you. Maybe a follow just to clarify, understand your answer to Suwon. So in your all these claims, your magic gate is also random. It's not a fixed, let's say.
Yeah. So at least for the provable cases, the magic gates are drawn from some exact design on a finite number of qubits, which we know can be generated exactly in exponential depth on a constant number of qubits, which is a constant, right? So, yeah.
Okay, I see. Okay, now as experimentalist, I have really naive questions.
Yeah.
Yeah, thank you for your talk. Now I see why theoreticians are so into these random circuits, because the relation maybe to quantum mechanics, to statistical mechanics. But my question is, like, when we think about the temperature, we always kind of think the entropy is changing as you are changing the temperature. So how should I think the entropy concept in the circuit? Because you are doing unitary evolution always, so the entropy.
Yeah, so you're asking how I should think of the
how should I
entropy of these state ensembles?
right.
Well, they have a lot less entropy than Haar random states do, and that's just apparent from the circuit depth, right? But so for instance, if I look at like the von Neumann entropy or something of some subregion, it'll be polynomially small in n. It won't be exponentially, the purity will be polynomially small in n, as opposed to being exponentially small for a Haar random state, right? So there's still like very entropic states, but I think the notion of state and unitary designs with relative and additive error is really about what you can measure efficiently, right? And so you could have a highly entropic state, but it may not be possible to tell the difference between that and a low entropy state.
Sure.
Yeah.
I see. Yeah. Thank you.
Thank you for the nice talk. Just for clarification, so do you apply the T-gate in the end of the circuit, or?
Yeah, it varies depending on the architecture. Let me actually go back to the first the slide where I just flashed both of the circuit architectures, because I think they. Okay, so for additive error designs, the architecture looks something like this, where you have Clifford gates that are applied, and then followed by some constant number of magic gates, and the initial state is some product state. For bounded relative error unitary and state K designs, the architecture looks like the sandwich architecture. So you first apply a round of magic gates, then you apply Clifford gates, then you apply magic again.
And
that's roughly what they look like. Yeah.
What happens if you first apply Haar random, one side Haar random, with your operators and then apply random Clifford.
Oh, and so which is, but you don't apply this last layer? Is that what you're asking? Yeah, that's actually a really good question, and I'm glad you asked because it brings me to my last one of my slides, which I'm always happy to discuss things I didn't have time to discuss. So so actually, it turns out that okay, so the left-hand side you can think of as basically the circuit architecture you're thinking about. Think of the green as being local Clifford gates that go for log depth, and the blue as being like the magic gates or some local random gates that you've applied. So it turns out that those state ensembles and also the unitary ensembles that you get, if you don't start with a product state, those actually can never, even when the Clifford depth is extremely large, those can actually never give you state and unitary designs with bounded relative error. They can give you, bounded additive error designs. The reason is, you can just ask what observable distinguishes these relative error state designs from hard random states, and it's basically this quantity which I'll call the stabilizer Renyi entropy. It's the purity version of that. So that actually distinguishes between these two things. So the fact that you have magic both at the beginning of the circuit and at the final time is actually really important for getting these relative error designs. And that's actually not something I understand very well in the StatMech picture. So the StatMech picture that I mentioned is very, clean for understanding these additive error state designs and just additive error designs generally. For relative error, I think it's we don't have such a clean picture.
Thank you for your answer.
Yes, thanks for the very nice talk. I just want to clarify from the StatMech argument, does this actually also give a lower bound? I'm just trying to make sure.
Does this give a lower bound? Yeah, the argument tells you that at least this way of thinking about how you get an additive error design doesn't make sense if you have constant circuit depth for the Clifford circuits, right? But I think that's been known through other arguments like in the literature before, or that is to say, if you just have constant circuit depth, I think it's very easy to cook up like say the stabilizer, Renyi entropy, or some other observables like purity, for instance, that tell you the difference between the state ensemble that you're generating and a hard random state, right? Okay, so this gives you some lower bound. I think more interestingly, it gives you quantitatively the number of magic gates that you need, which matches what we can prove. That might also be a lower bound, I guess. Yeah.
Sorry.
Yeah.
But you say that matches what you can prove. That sounds like it is a lower bound, or what you can prove that.
Yeah, what we can prove, I don't know if what we can prove is like optimal, right? That is to say, but the argument suggests that it should be, right? Like you can't do better than order k squared parametrically in k.
Right.
Yeah.
Okay. That's the question. And can I also ask, am I understanding correctly? This is like infinite sample limit. So do you have a sense of how many samples would be required if we actually want to implement this?
What do you mean infinite samples? So k is the the Haar moment that you're.
So you're drawing from like some ensemble of random.
Finitely number of times.
And you're averaging over some like a finite depth circuit construction.
Exactly.
Is that average how many? If you're actually doing this, let's say experimentally. How many samples are
how it converges basically. To this how the convergence properties are for this ensemble.
Yes.
Yeah, that actually don't have I don't have anything to say about that. I think that's basically related to how well it would form a 2K design or something, right? If you're controlling the variance. So I don't think it actually matters that much. As long as k is constant,
I see.
Right? Yeah.
Thanks.
I have another question, also maybe relevant to Suan's. So based on current theoretical understanding, if you have, let's say, a fixed T gate and other, let's say, Clifford Haar random gate, could I just use fixed number of T gate to construct any magic Haar random gate?
Sorry,
it's more like because if I understand correctly during this in your talk, the proof why you kind of not fixed your magical state into a specific one. So my question is, if I just have some random magical state and I just allow you use, for example, T gate and any other Haar random Clifford gate, could I just have a use finite number of all this T gate combined with other Clifford gate in order to construct any magic state?
I think the statement is to do anything with bounded relative error, so small multiplicative error, you need a number of magic gates that does grow with system size, right? It can be applied in it's a constant depth application of magic, but it still has to grow with n, right? Yeah. Oh, yeah, maybe I missed the. Oh, okay. Yeah. Okay. Yeah.